Welcome to Mission Control, everyone. I am your flight director for today's explainer, and we are going to run a high-stakes flight simulation for one of the absolute most critical missions in the Cambridge syllabus, Probability and Statistics 2. Specifically, we're locking our navigation coordinates directly onto the Poisson distribution. Right now, I want you to treat your next past paper as our primary objective. The goal? A perfect, full-mark touchdown. But we have a serious problem. The pre-launch telemetry is coming in, and it's showing that way too many candidates are crashing and burning on the easiest questions. It's a massive loss of points. So we are going to treat this exam paper exactly like a complex flight system that requires perfect, rigorous execution. We are going straight into the examiner's playbook to decode the exact telemetry they use to grade you. Strap in. Now, this is the question that should be flashing bright red on your radar. Why do so many well-prepared candidates miss the absolute easiest marks? To understand this systemic failure, let's take a look at two pilots currently running in our simulation. First up, we have pilot Alex. Alex overcomplicates data calculations, burning way too much exam time and mental fuel on simple approximations. He's overthinking it. Then we have pilot Sam. Sam has a different issue. Sam ignores structural boundary constraints completely, risking a total systemic breakdown simply because the answers aren't formatted correctly. Both pilots are incredibly smart, but neither actually understands the examiner's perspective. Today, we are going to fix that. We are mapping out a flawless trajectory so you can completely avoid the critical mistakes that Alex and Sam are making right now. All right, here is our exact flight plan for today. Section 1 is core Poisson principles. Section 2 is the method mark strategy. Section 3 covers top examiner warnings. And we bring it all home in Section 4 with deconstruct, solve, evaluate. Let's go ahead and initiate the launch sequence. Section 1, core Poisson principles. Think of this as your primary engine thruster. The Po-lambda distribution model is built on one foundational, completely non-negotiable rule. The mean equals the variance, which equals lambda. If you do not have this locked into your system architecture, your flight is grounded before it even begins. It's that crucial. The Cambridge syllabus explicitly emphasizes that top-tier candidates exhibit a connected conceptual understanding of this exact rule. This isn't just about casually memorizing a formula, it's about knowing that this entire theoretical architecture rests on precise definitions and causal relationships. You absolutely need to be able to transfer this rule to entirely unfamiliar context, especially when the exam throws a massive curveball at your trajectory. And this brings us to our first major hurdle in the approach trajectory. In our simulation, we can see pilot Alex attempting to navigate the space between standard Poisson distribution rules and using Poisson as an approximation to the binomial distribution. Alex is sweating, overcalculating, and burning through precious fuel because he's treating them as entirely separate galaxies. But the principal examiner reports tell us that comparative analysis here requires identifying both similarities and differences. You must use comparative connectives and draw conclusions fully supported by evidence. It's all about knowing your system parameters. For instance, when n is large and p is small, you shift smoothly from binomial to Poisson. Recognizing these command keywords as system parameters will instantly clear your orbit and save you massive amounts of time. To prevent a total system overload during the intense stress of the actual exam, we are initiating a navigation override right now. I challenge you to actively create a custom mnemonic using the first letters of key Poisson terms. Think mean, variance, lambda, approximation, binomial. Go ahead, lock this memory hack into your mental dashboard. This kind of active engagement is your emergency backup system. When the time pressure hits and the cabin shakes, your brain will effortlessly retrieve this interconnected web of terms, ensuring maximum retention and keeping your flight path completely stable. Moving forward into our mid-flight check, Section 2, the method mark strategy. Attention all crew, we have a critical alert incoming directly from the principal examiner reports. But wait, before we fire the secondary boosters to secure those maximum marks, I am pausing the simulation. You need to optimize your flight path right now. Subscribe to Ace the Exams at the handle @AceTheExams right now and turn on all notifications so you never miss a mission update. Okay, resuming simulation. Listen to this massive insider tip. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Method marks are literally your parachute. In our simulation, pilot Sam just completely botched a calculation. But because Sam showed the entire working process, the examiners awarded partial system credit. Method marks are a procedural framework that rewards your underlying logic, not just your final destination. So, the absolutely crucial point here is that you must respect the structural boundary constraints. In our simulation right now, the crew has just encountered a critical roadblock mid-paragraph. Their evidence links are completely failing and the system is crashing. I am overriding the console and injecting the Peel structural template to save the trajectory. Point, evidence, explanation, link. You must adapt this by using proper headings to make your point, correct terminology as your evidence, appropriate formats for your explanation, and clear annotation to link it all together. The examiners are scanning your paper like it's raw machine code. If you don't format your presentation of information according to these strict conventions, the examiner's radar simply cannot detect your logic, and you will bleed marks. Follow these rules, and you seamlessly rack up those vital procedural marks. We are now approaching a known hazard zone. Section 3, Top Examiner Warnings. Let's run a quick debris detection simulation based entirely on historical crash data from past Cambridge candidates. The principal examiner reports have flagged 3 specific catastrophic errors that happen year after year. Your job as a pilot is to spot these hazards before they take down your exam score. All right, here is the debris on the radar. Rapid fire time. Mistake number 1, confusing cause and effect. Students constantly mix up their variables in Poisson word problems. Mistake number 2, forgetting to check format and presentation. As we just discussed, sloppy working means 0 method marks, period. And mistake number 3, answers are not specific to the given context. If the question is about cars arriving at a toll booth, your final analytical evaluation must actually talk about cars and toll booths, not just abstract numbers. Evaluation of evidence quality requires identifying limitations and checking if your math makes sense in the real-world scenario provided. Avoid these 3 pieces of debris, and your flight path remains completely clear. Initiating final approach. Section 4, deconstruct, solve, evaluate. Let's see how this all builds into our ultimate touchdown sequence. Top-scoring candidates do not just guess. They use a rigid 5-step procedural framework. Step 1, identify given information. Extract the exact data from the noise. Step 2, break into logical steps. Set your flight path. Step 3, solve systematically. Execute the math flawlessly. Step 4, check reasonableness. Look at your answer. Does a lambda of 500 even make sense for this specific scenario? Step 5, justify with evidence. Anchor your answer in the specific context of the question. This deconstruct, solve, evaluate loop guarantees analytical depth and completely prevents those superficial, rushed answers that cause Pilot Alex and Pilot Sam to lose their way. By applying this sequence, our pilots in the simulation have just confirmed a successful full-mark touchdown. Before we complete the full debrief, let's do a quick systems check on what we've built today. We've mapped out the foundational theories, established the critical safety net of method marks, cleared the historical debris from our path, and locked in a reliable 5-step framework. This is our pre-flight question scan checklist. But wait, I have one interactive radar challenge left for you. Can you instantly recall that custom Poisson mnemonic you created earlier in the mission? Think about it. If you can instantly pull that up, your memory architecture is holding incredibly strong. Mission accomplished. We have successfully distilled the examiner's playbook into a reliable set of flight protocols. You now have the exact telemetry needed to avoid crashing on easy marks. But before you disconnect from mission control, it is vital you take action. Subscribe to Ace the Exams at the handle @AceTheExams. Enable the notification bell so you never miss a pre-flight briefing, and drop a comment below sharing your specific subject and tier. Now, I leave you with this final thought. When you sit down for your actual exam, will you be flying blind like our pilots were at the start? Or will you use this exact playbook to navigate your way to top marks? The flight path is yours to choose. See you in the next explainer.